Hello there, welcome to this video where we're going to take a look at a mathematics problem that I've chosen from a sixth term examination paper. So we're going to be going back to the 1987 sixth term examination paper, step 3 paper. And it's going to be question 3 that we're going to be looking at. So I'll leave a link in the description to this video so that you can download the paper if you need to. And you can see the problem for yourself. And you can download any other step papers that you want to download. If you are preparing for to do a step paper, if you're planning to do a step paper over the next couple of years or whatever, even going back as far as 1987 is well worth taking a look at some of those papers. The problems are, in my opinion, considerably more challenging than the types of problems that you're going to get on the more recent step papers. Now, obviously, that is partly to do with changes in specification material. So some of the stuff that came, that was expected, that was taught on the A-level maths and further maths courses back in the 1980s, would have been slightly different to what it is now. Nevertheless, if you are planning to do a step paper, it shouldn't put you off that from time to time you expose yourself to problems that involve material that is not strictly on the specification, that you don't strictly need to know. As far as I'm concerned, the only thing that should determine what you do and do not learn is yourself. Okay? No specification really should be dictating to you what you should and should not be learning. Generally speaking, though, those people that are going to be most successful when it comes to doing a step paper will be those people who have a natural tendency to learn, to go beyond the specification. So if going beyond the specification is something that kind of freaks you out a little bit, you're not too comfortable with it, or you kind of balk at the facts, then really consider whether doing a step paper is the right decision for you to be making. Because there'll be plenty of people that will be doing step papers and applying to high-ranking universities who will be more than happy to go beyond the specification and learn whatever they need to learn in order to succeed. Make sure that you're one of those people. Okay, so let's have a look then. So this is quite a challenging problem. It took me a while to think about some of this. How to solve some parts of this. It's a kind of strange problem. There's two parts, well, 3 parts really. The first part doesn't really seem to come into the other 2 parts in a significant way, unless I've missed something. But for part A just seems to be kind of separate from part B, which is kind of unusual because usually there's a bit of continuity. There's a bit of flow through the problem. The problem tends to tell a bit of a story. Not so in this case, but nevertheless, it's still a nice, interesting little problem. So, what we're told is, if z equals x plus iy, so we're dealing with complex numbers here. This step 3 from 1987 it was kind of concentrating on further maths. So it will involve things like complex numbers, things like that. So x and y are real. And we need to show that the modulus of x times cos alpha plus the modulus of y times sine alpha is less than or equal to the modulus of z, which is in turn less than or equal to the modulus of x plus the modulus of y. Okay. So, what I would do here is consider, on the one hand, not necessarily in this order, this inequality and this inequality. Okay, in fact, I went for this inequality. I originally set about this inequality first. So the modulus of x cos alpha plus modulus of y sine alpha is less than or equal to modulus of z. But I ended up doing this inequality instead somehow. I don't know how, but okay, we've got modulus of z. which is equal to the square root of modulus of x squared plus modulus of y squared. So this is just definition of modulus of a complex number. Okay, maybe you could argue modulus of a complex number, z equals x plus I, y is more square root of x squared plus y squared, but remember, x and y are real, so the modulus of x squared is going to be equal to x squared. It's not going to make any difference fundamentally. So this is maybe arguably the definition of modulus of z, but this is equivalent to that definition. So we're going to use this for the simple reason that we've got modulus of x and modulus of y up here. Okay, and that is going to be less than or equal to modulus of x squared plus twice the modulus of x times the modulus of y plus the modulus of y squared. Okay? Which is, this in turn is equal to the square root of the modulus of x plus the modulus of y all squared, which is equal to modulus of x plus modulus of y. So we've got the modulus of z is less than or equal to modulus of x plus modulus of y. So we've proved that inequality. That's nice and easy. Okay? And I'm going to have to refer to my notes because I can't remember what I did for the next part. Oh yeah, I can. Right, so then modulus of x cos alpha plus modulus of y sine alpha. So I had to have a bit of a play around with this initially until it clicked what I needed to do. Think trigonometry when you do your A-level stuff. So you do the r sine theta plus alpha sort of forms for trigonometric, certain trigonometric expressions. That's exactly what we've got here, right? So this is going to be equal to, what is r equal to? It's the square root of modulus of x squared plus modulus of y squared. And it doesn't matter whether we choose cos or sine or whatever, to be honest with you. Let's go for sine. It's going to be sine alpha plus, this alpha here, by the way, is not the same as this alpha. So it's going to be alpha plus some constant. And the constant might be positive, it might be negative. We don't really care, actually. But this in turn is going to be less than or equal to what? It's going to be less. Notice that sine alpha plus k, that's always going to be less than or equal to 1. Okay? So this is always going to be less than or equal to the modulus of x squared plus modulus of y squared, which is equal to the modulus of z. Therefore, modulus of x cos alpha plus modulus of y sine alpha is less than or equal to modulus of z, which in turn is less than or equal to modulus of x plus modulus of y. So we proved that inequality as well. So putting all of these together, we get the series of inequalities that we require up there. Nice and easy. So the only thing that I had to wait, kind of hang on for until it popped into my head here was this, really. This I've done plenty of times before, this kind of thing. So this is kind of similar to the triangle inequality, which you might not come across too much at A-level now, but it's a very important inequality in mathematics, the triangle inequality. For this one, I just had to kind of sit around and think for a couple of minutes until I realized that you could do this. That's how it is sometimes. You've just got to be a little bit patient. You've got to stare at something enough until you figure out what to do with it. Okay, so let's have a look at part B now. This is where things start to get a little bit trickier, although not too tricky. Surprisingly straightforward for a step paper. On this step paper, 1987, I've done a couple of the other problems on this, and they are much more difficult. The first question on this, which I've done a video for, I don't know whether I will have uploaded it by the time I've uploaded this video, but it's an awful question in so many ways, but so thoroughly enjoyable. Once you get the solution, Just the details that you've got to iron out, it just takes a long time. But once you get there, I've made the video, I will upload it sometime, and you'll see at the end of the video just how exasperated I am with the problem. But that's the sign of a good problem. If you feel absolutely exhausted when you get to the end of it, but you've got a solution, that's you've learnt a lot when you've done that. Okay, so we're done with that now, actually. I don't even think we need that anymore, so let's get rid of that. Right, so now we've got, by considering 5 minus I to the power of 4 times 1 plus I, show that pi by 4 is equal to 4 inverse tan of 1/5. Oh, let's write it properly, John. 1/5 minus, is it plus? Minus inverse tan of 1 over 239. Okay. So how could you go about this? Because all it says is by considering this. Okay, by considering this. Well, there are some clues there. There are some clues in what you've got here and what you've got here. And it's important that you pay attention to those clues, by the way, because it's going to be important for what we have to do next, which does actually follow on from this. It extends this idea a little bit. It's important that you pick up on a certain pattern, in my opinion, in order to do the next part. You won't be told, you're not told what the pattern is that you need to spot. That's for you to figure out. And that's the whole point of step papers, okay? That you are the one that is responsible for doing the hard work. Okay, so what's one of the clues? Well, one of the clues is that the argument of 1 plus I is equal to pi by 4. Okay, how do we calculate the argument of a complex number? So if we've got x plus iy, then it's going to be related to inverse tan of y over x. Okay, it might be, we might need to add a pi or something like that onto it, but generally speaking, the argument of a complex number is going to have something to do with inverse tan of y over x. And what we're looking for really is the angle starting from the horizontal, the real axis, and working around in a anti-clockwise direction. So if our complex number is here, this is x plus iy, then we draw a line to the origin, and that's the argument. This angle here is going to be theta, which is going to be our argument. But notice that that angle is greater than 90 degrees, which inverse tan is limited to values between minus 90 and 90, or minus pi by 2 and pi by 2. Strange that I should go into degrees, actually, because we're working in radians here, but anyway. So you might have to just kind of manipulate the expression a little bit. If you're used to dealing with complex numbers, you'll know what I'm talking about. If not, then if you're not too familiar with complex numbers, then spend a little bit of time working, just finding out about complex numbers and arguments and things like that. I'm not going to go through it in this video because it's not the intention. But do your own little bit of independent research. It's always a good thing to do. So this, on the other hand, right, so let's have a think about the argument then of, and not 5 minus I to the power of 4, it's going to be 5 minus I that I'm going to consider. So it might help for me to kind of visualize where this is going to be. Well, 5 minus I is going to be kind of down here somewhere. So the argument is going to be this angle, so it's going to be beneath, it's going to be below the horizontal axis. So I can either do inverse tan of minus a fifth, or I can bear in mind that this is going to be equal to minus inverse tan of plus 1/5. Okay, so I'm just using kind of trigonometric relationships of trigonometric functions here to get rid of the minus. Because notice here I've got inverse tan of 1/5. Okay, so by de Moivre's theorem, de Moivre's theorem, or whatever, there's other ways that you can kind of think about it, but the argument of 5 minus I to the power of 4 is going to be 4 times the argument of 5 minus I, which therefore is going to be minus 4 inverse tan of 1/5. So the clue here now, in my opinion, is to actually multiply these together, to actually find out which specific complex number in the form x plus iy is this equal to. Okay, so it does take a little bit of work, but it's not too onerous really. So let's have a look then. 5 minus I squared, for example, is going to be 25 minus 10i minus 1, which is 24 minus 10i, which is what, 2, 12 minus 5i. So 5 minus I to the power of 4 is going to be this squared, which is going to be 4 times 12 minus 5i squared, which is 4 times 144 minus 120i minus 25, which is 4 times 144 minus 25, 119, 120i. So 5 minus I to the power of 4 times 1 plus I is equal to 4 times 119 minus 120i times by 1 plus I, which is 4 times 119 plus 119i minus 120i plus 120. Aha, okay, yeah. Which is 4 times 239. That's a good sign. Minus I. So let's have a think of what that is going to look like. It's going to be a complex number. It's going to be down here somewhere. It's going to have quite a small argument. It's going to be just kind of below the horizontal, so to speak. So again, the argument is going to be inverse tan of minus 1 over, okay, maybe minus 4 over 4 times 239, but I can ignore the 4 by similar triangles, and I get inverse tan of minus 1 over 239. So again, using properties of tan, then I get that the argument of 5 minus I times 1 plus I is going to be minus inverse tan, 5 minus I to the power of 4 is going to be minus inverse tan of 1 over 239. So now, when you multiply complex numbers together, so if you've got the argument of z times w, this is equal to the argument of z plus the argument of w. Okay, just one of the properties of complex numbers and arguments of complex numbers. So in other words, the argument of 5 minus I to the power of 4 times 1 plus I, which is minus inverse tan of 1 over 239, is equal to the argument of 5 minus I to the power of 4 plus the argument of 1 plus I. And a little bit of a rearrangement there gives pi over 4 is equal to 4 inverse tan of 1/5 minus inverse tan of 1 over 239. Okay, job done. That's the first part. And now we've got another part that's kind of similar to this. but we're given an expression similar to this expression here, but we're not given the what to consider part. We've got to figure that out for ourselves. So, but we've got to look for the clues, I guess. So I'm going to leave this up here so we can I can kind of demonstrate what I'm talking about. So the new expression that we need to prove is that pi by 4 is equal to 3 inverse tan of a quarter plus inverse tan of 1/20th plus inverse tan of 1/1985. Who knew, right? Who knew? Okay, so the clues are here. 5 minus I to the power of 4. Kind of match things up a little bit. You've got the 4 here, which kind of corresponds to the power. The 1, which corresponds to the real part, and 5, which corresponds to the imaginary part, and 5, which kind of corresponds to the real part in some way. Similarly, with the pi by 4, we've got inverse tan of 1. And if you remember, when I calculated this, it was 4, what was it? 239 minus I. So again, we've kind of got the coefficient here corresponds to the power. 1 kind of corresponds to the imaginary part, 239 to the real part. And it's this pattern that's really going to lead us to what it is that we need. So what I would imagine here is that this is going to correspond to something like possibly either 4 plus I or maybe 4 minus I to the power of 3. This is probably going to correspond to something like 1 plus I again. Possibly 1 minus I, but I'm going to leave it as 1 plus I. And this is probably going to correspond to something like 20 plus I or 20 minus I. And this is going to come from the product. So if I just use, for example, maybe 4 minus I cubed times 20 minus I times 1 plus I. What I'm looking for is when I expand this a suitable product out that looks maybe something like this, that I'm going to get something like 1985 plus or minus I. So maybe plus I or 1985 minus I or some multiple of that. Okay, so how can I narrow things down? How can I figure out which one it's going to be? Well, I've just got to be prepared to try things out, you know. That's how it is sometimes. You've just got to mess around. Actually, this is the combination. This is the right combination. This wasn't the first one that I tried, though. Understand that. The first combination that I tried was 4 plus I cubed times 20 plus I times 1 plus I. I did initially try that. Well, I started with this, and I quickly something quickly made me realize that this wasn't going to work. I think it's because you kind of get the impression that you need some negatives in there, otherwise the real and imaginary parts are just going to get gradually bigger and bigger and bigger. So you kind of do need some negatives in there. So then I tried this. And it really is just playing around with things until something works. But the motivation for this is spotting that pattern, observing that pattern. That's what you need to do. And then once you've realized what you need to do, you can either just get on with it, or if you think it's too long, you can whinge about it and get nowhere. Or if you really think that there's a better way of going about it, then try to find a better way. Okay? But sometimes it's best just to get on with things. So, 4 minus I cubed, let's see. 4 minus I squared is 16 minus 8I minus 1, which is 15 minus 8i. So 4 minus I cubed is going to be 15 minus 8i, 4 minus I, which is 60 minus 15i minus 32i minus 8, 52 minus 47i. I hope I'm not making any mistakes here. So then we need to multiply that by 20 minus I. 528, 1040 minus 52i minus 940i minus 47, which is 1040 1040 minus 47 is going to be 993 minus 992i. Now this is good because these are quite close together, 993 and 992. This is another sign really that you're kind of going in the right direction, I suppose. So then we get 993 minus 992i times 1 plus I, which is going to be 993 plus 993i minus 992i plus 992, which is, of course, 1985 plus I. Aha. Okay, and then it's a very similar thing to what we've already seen, right? So the argument of 1 plus I is pi by 4. The argument of 4 minus I cubed is equal to minus 3 inverse tan of a quarter. The argument of 20 minus I is equal to minus inverse tan of 1/20th, and then the argument of the whole lot is going to be inverse tan of 1 over 1985. Hope that's right. Yeah, because then we get the, I'm going to write it all out actually. I'm just going to have 1, 2, 3, 4. So we get 4 is equal to 1 plus 2 plus 3. And therefore we get pi by 4, which is 1, is going to be equal to, subtract 2 and 3 from each side, and or add even, whatever. Then you get your 3 tan, inverse tan of a quarter plus whatever we need. So it's a very similar argument, but it's really just picking up on that pattern and exploiting that pattern that you've seen from the first example, which was a bit more guided, and then you kind of let loose and you're on your own. So you're given what to aim for, whereas before you were given not only what to aim for, but what to consider in the first place. This time you're just given what to aim for, and you've got to figure out what to consider. Now, it can be quite sneaky sometimes when it comes to STEP, because you can be given an example to do something, and then given something that looks very similar, but actually the way that you approach it is considerably different. So don't always rely necessarily on the pattern being quite so close as it is here. It's nice when that happens, but it doesn't always happen like that. So if you haven't already done so, by the way, I'd be really grateful if you could show your support for this channel by subscribing, hitting the subscribe button, and giving this video a like. If there is anybody that you know that is preparing for STEP or MAT or anything like that, and you think that these videos would be useful to them, please forward these videos on. I'm trying to reach a wider audience. If you yourself are preparing for STEP or MAT or your maths or further maths exams at A-level, and you want some extra support, you would like some extra support, some extra guidance, then please get in touch. I'd love to hear what your needs are, what your requirements are, what your expectations are, and have a discussion with you about how I can help you. I'd love to see you go into your exams with the confidence of knowing that you're going to absolutely smash your exams and that you're going to secure your place at university or wherever else it is that you're wanting to go. I'd love to help you get there. So please feel free to get in touch. So that brings us to the end of this problem, and it brings us to the end of this video. Thanks a lot for watching.